So at this time, I would now like to begin the student presentations. The first team is from the University of Alabama. Their team name is the Crimson Transit. They will be presenting today on dual mode transit, proposing combined utilization of road and rail networks to increase transit accessibility in Cuba. So definitely reliving some of the previous discussions with Dr. Julio Cesar. The team is composed with Elizabeth and Preston. Their faculty advisor from the university is Dr. Stephen Jones, and they were mentored by Eric Sibila as their CISC industry advisor. So without further ado, let's welcome Elizabeth and Preston.
Hi, so first we want to say thank you for bringing us down. We are really excited to be here. I'm Elizabeth Hartzog, and I graduated from the University of Alabama in December with a degree in civil engineering, and I now work for HNTB as a transportation engineer in Raleigh, North Carolina.
Hello, my name is Preston Judy. I'm a current master's student in civil engineering with a concentration in transportation systems engineering at the University of Alabama. And come June, I'll be starting work as a civil engineer in training in transportation planning and traffic operations with Kimley Horn Associates in the Northern Virginia office. Together, we make Crimson Transit. And today, we want to discuss with you our idea for the combined utilization of road and rail networks to increase transit accessibility in the city of Havana. We call this dual mode transit. First, we will discuss a few key background issues that we feel are important to understand our concept. First, we'll talk about transport issues in Havana. Then we'll discuss the general concept of dual mode transportation, also high rail vehicle technology, and then finally, some key assumptions and considerations we took into account for the design of our project. Next, we'll get into the design and analysis phase of our project, where we'll discuss the technical design of our transit corridor using geographic information systems, as well as the service area we projected, including populations of who we might serve with this project. Finally, we'll get into future plans, including the testing and expansion phases of our project, and key partnerships we believe can bring this to fruition.
So in order to best describe our reasoning behind picking a dual mode transportation as our subject for the project, we wanted to give you some background information on the current transportation issues in Havana. In May of 2016, Preston and I had the privilege of studying with the University of Alabama at CUBA, the engineering university in Havana, and through our experience in the classroom and in the field with the professors studying air quality, transportation, and the engineering's effects on society and culture, we observed that the existing public transportation options were less than ideal. Buses are the cheapest and most used option among the residents in Havana and are extremely over capacity at all times and consist of inconsistent wait times, causing distress among its passengers. The government's chosen solution to the bus issue was to distribute more taxi certifications to the public in order to relieve the issues. This led to more choices, but the government did not regulate the fares or route, which resulted in drivers favoring the heavily tourist areas and higher route fare options, creating taxi deserts in the areas of Havana that so desperately need the affordable options. You may be asking why there's so much discussion among the different forms of transportation, and this is why. And the reason due to this is because car ownership is less than 0.04 cars per person in Havana. We felt that there needed to be a more creative and innovative approach for this project. Dual mode transportation is best understood as a route design, and why we chose this method was because dual mode transportation systems take one vehicle utilizing two modes of transportation consisting of road or rail, road or air, or road and water. The picture to the right is an existing vehicle in Hokkaido, Japan that is accessible to both land and rail. The benefits of doing this is that it uses existing infrastructure not currently used for transit without reducing the lanes, which after last year's presentation in which I submitted a project on bus rapid transit systems, we realized that was one of the major pitfalls, as it may create more issues than resolve them. And as mentioned, dual mode transportation needs adapted vehicles capable of operation on road and rail. High rail vehicle technology makes this happen by converting road vehicles to rail vehicles. And while in use, the rolling stock is tucked away out of sight, but when needed can be easily employed. Harsco Rail, one of the major manufacturers of high rail vehicle technology, was contacted to get estimates on what the price may be to convert these vehicles to a high rail vehicle. And no response was given. However, we found limited data online, and that said prices would be around less than $10,000 for a 5-passenger vehicle, such as an F-150 to the right, and for a medium-duty truck, as shown in the lower right, would be around $40,000 to $50,000, and a heavy-duty truck, which would be a Freightliner, would be around $100,000 to $300,000. And to calculate the potential ridership, we use the projected numbers from last year's bus rapid transit submittal to serve as a benchmark for our dual mode transit project.
We want to note that we did consider a few different important assumptions and considerations in our project. The major assumption, I would say, is the fact that this general concept is feasible using existing infrastructure, particularly the railroad network in Cuba. We do understand and have some concerns related to that rail infrastructure that we will address later in our presentation, as you might have yourself. But in order to continue forth with the route design itself, we had to assume that this is feasible in general. Next, we had to decide what's considered walkable. Different literature, as well as some experience I have with transportation, suggests that the upper threshold of what someone is willing to walk to some form of transit is around 1,600 meters or a mile. So we chose that threshold to move forward with our route design. And finally, we decided that the average population density would need to be representative of a municipality. We understand that from city block to city block, this might not be perfectly accurate. It could overestimate in some areas while underestimating in other areas, but we felt it was appropriate to move forward with a more detailed analysis of our service area population.
Before Preston gets into the route and design methods, we felt you may be wondering why we chose the Independence Corridor as our option. We had 3 criteria that we designated that would be of extreme importance to this project, and that was 1, it would be close to CUHI, 2, it would reach the downtown core, and 3, it would be a major arterial road running next to an existing railway system.
Now, as you can see, and as I will discuss, Avenida de la Independencia fits the bill in all 3 of those categories. Now, we took a more qualitative approach in how we chose the corridor, but we knew we wanted to take a more technical geospatial approach using geographic information systems for the actual route design of the project. You can see here our corridor fits the bill. The blue line represents Avenida de la Independencia. It's a 6-lane major urban arterial roadway, 3 lanes in each direction, northbound and southbound, for the majority of its 8-kilometer expanse. And in red, you can see a nearly parallel railway almost along the entire corridor, both being approximately 8 kilometers or 5 miles. Additionally, there are various railroad crossings in between, which we will discuss how they will function within our system, that are an important key aspect of going between the 2 different modes of transportation. Now, beginning with our design process, how we went about that was using satellite imagery as a reference. Data is notoriously hard to get, especially in great detail with good spatial resolution in Cuba. Due to the satellite imagery available. So we zoomed in as clearly as we could and as closely, went through and visually inspected, and starting towards the south near CUHI, went through and built our line shapefiles segment by segment, inspecting each satellite imagery, pieces of the satellite imagery to make sure it was accurate as possible. Because of the nature of satellite imagery, it's actually a mosaic of various images captured from different dates, so we felt most comfortable going through and visually inspecting this corridor to ensure its accuracy. We did so for both the roadway and the railway, as well as the various railroad intersections, and visually confirmed that. As you move in closer, you begin to see some of the issues related to the spatial resolution. The closer you get in, the harder it is to see some of those certain details. Under this red line that represents our railroad, there could be 1 track, 2 tracks, 3 tracks. There could be various informal crossings. There could be things that we are unable to detect. We knew we wanted more detail in order to confirm our rail networks that we were building in our road networks. So using open source data through OpenStreetMaps, we actually were able to import an additional road network represented in the geospatial network, as well as a rail network for the greater Havana region. Doing so and crossing these two modes of transportation, we were actually able to find an additional 6 railroad crossings in addition to the 15 we found through visual inspection, creating a total of 21 railroad intersections with our road network on our 8-kilometer corridor. And this is our northern terminus of the portion, getting into that urban downtown core that we mentioned as one of our 3 categories, just south of the Jose Marti Memorial near the urban core. Here's our southern terminus, just east of CUHI, the National Technical University. And this is where I want to draw attention to our railroad crossings. These are what we refer to as multimodal transfer stations. This is where our vehicles can go between our 2 modes of network, between the blue line, which represents Avenida de la Independencia, the road network, and the red line, which is our rail network, to combine that. This is where the high-rail vehicle technology can be employed, and the vehicles can go from rail to road or from road to rail, depending on the conditions of traffic. We do want to note that while there are 21 railroad crossings, and these are transfer stations, they are not stations in the sense that every single one of them would be stopped. It's stopped at when on the ride. We are intending for this to perform much more similar to personal rapid transit, where, for instance, 5 or 6 students, depending on the vehicle size, if it were for example, the chassis of an F-150 truck or a small SUV, could get into a small personal vehicle with similar or same destinations along the corridor and can stop at a few shared destinations, skipping most of the stops along the way. Because we want to maintain small vehicle sizes, we believe that we can actually go around and use the network much more fluidly rather than putting a large-scale train on there and dealing with some of the issues related to that. We felt that would help us avoid some of the pitfalls of bus rapid transit and light rail, where you are stopping at every single route and not actually getting to where you want to go fast. Next, we went back to what we thought was important for this project. We wanted to see, can we actually potentially reduce traffic congestion along Avenida de la Independencia? After all, it is a major urban arterial roadway. And additionally, can we increase transit accessibility, and for who? So, we don't have a lot of examples of dual mode transit. There's a very small system in Hokkaido, Japan, as Liz mentioned earlier, but we don't have a lot of data or information to go off of to compare this of who we can serve, where can we get ridership projections, and how can we go about that process. So we decided to figure out who we serve and who can access this transit system without deteriorating the current roadway system. And so we decided that meant who can walk to it. So using ArcGIS's network analyst tool, we input the 21 different multimodal stations, or the railroad crossings, as our facilities, and then using that tool, we were able to generate out, along the road network, the walking distances that someone could access our system. In green, you can see all of the areas within 800 meters walking distance along the road network, and then in yellow, it extends it out to 1,600 meters. Now, according to our calculations, this gives us a total service area, meaning walking distance within our transit corridor, of approximately 21 kilometers. Going on from that, we wanted to know who can we actually serve in this area. We didn't want to just take 21 kilometers, compare that to Greater Havana, and assume that was a proportional representation of the population. We wanted more detail. So we went to the National Statistics Office from Cuba, took the total square area of each of the municipalities that our service area intersects, took the total population of each of those municipalities, the information is from the 2010 census, and calculated the average population density of each municipality. We then, comparing it to its representation in our service area, found each service area population for a total service area population of approximately 144,000 people. So that's to say, 144,000 people, we believe, according to our calculations, could access this dual mode transit corridor by simply walking. Now, as Liz referenced earlier, we used her bus rapid transit project as a benchmark of what we could achieve for daily ridership in the past if we want to achieve maybe similar numbers to other examples of transportation in other places in South America as well as North America. If we were able to achieve Miami's level of 2% daily riders, we could get just shy of 3,000 daily riders in this corridor. Bogota, almost 30,000 riders. And if we were able to match Curitiba's numbers of over 60%, this corridor alone could have over 90,000 daily riders.
And now that we've discussed the background and route design, we felt like it was very important to discuss the next steps in the process and how to make these plans a reality. First and foremost, it would be necessary to establish a joint institute between CUHI and the University of Alabama, as we have strong existing relations. It would be through this that would pave the way for dual mode transportation. sorry, go ahead.
And through this institute is where the research and testing phase would really begin, where a lot of the work for this will begin. If you remember back to the assumptions and considerations portion of the project, I mentioned this is where our key assumption was that this is feasible on the existing railroad network in Cuba. There are infrastructural and maintenance issues on the railroad network, as was pointed out in a previous presentation, and we do take this into account. We think it's vital that we were able to use geographic information systems, so in our research and testing phase, we can begin to collect this information by segment, railroad crossing by railroad crossing, and create a centralized database in our actual file that we've created for this project and continue to take that forward throughout the design process. In the information that we look through, we believe a low capital cost upgrade to a railroad crossing, for instance, with basic pedestrian signaling and pavement markings could be as low as $30,000, or for a complete reworking with complete automatic detection, including automated gates, could be between $250,000 to $300,000 per railroad crossing, depending on the Department of Transportation information you get your data from. From this picture, you can see our service area is just a small sliver of the greater Havana region and just a small part of the railroad network in the greater Havana area. We believe by working forward with this testing phase, we can then open our corridor up to the Havana residents, and beyond that, continue this research and testing phase using our system, expand it to the rest of the greater Havana region, and then eventually to other major cities in Cuba.
And this is a list of every potential partnership that we thought of that could help in making these plans a reality. We want to emphasize, though, that we believe that working with the existing relationships we have within academic institutions is the best way to go in order to make these plans.
Today we've discussed with you our idea for taking the combined utilization of road and rail networks to increase transit accessibility in the city of Havana, Cuba, through our idea of dual mode transit. We think it's very important that a new, innovative approach is taken to solve some of these issues. More buses, more taxis, more cars mean more of the same problems. We think that dual mode transit can increase transit accessibility and can increase mobility for the residents of Havana and beyond, and we do not think there's any reason that Cuba cannot or should not be at the forefront of transportation innovation, and we hope that dual mode transit and Crimson Transit can be a key partner in that process. Thank you, and we'll now take any questions.